I am excited to be here, so I will tell you about my work on Fortran standard parallelism in games. So to start, I would like to emphasize that as a theoretical chemist, the overarching goal for me is to enable theory and computation-driven chemical discovery, but that heavily depends on the availability of computational software. And quantum chemistry equations can provide solutions to the electronic Schrödinger equation that can accurately describe correlated molecular systems at very high accuracy. However, it is very well known that quantum chemistry methods have very steep computational scaling. And for them to be practically useful, we need to solve this computational bottleneck of these methods to enable accurate quantum chemistry calculations on large molecular systems. And the way I would like to tackle this problem is by developing new computer algorithms for newly emerging hardware. I also want to mention the importance of computer hardware and their role in quantum chemistry calculation. So previously, most of the computational power on the largest supercomputers would come from the homogeneous computer systems, and our ability to do quantum chemistry calculations were heavily limited on some small-sized organic molecules so that we could study some reaction mechanisms and so on. But we know that newly emerging hardware are all powered by some kind of accelerator. And so in order to actually take advantage of these hardware to do computational chemistry faster on larger molecules, for example, proteins, one needs to write different types of code that would actually run on these architectures. And by far the most popular platform to run on GPUs is CUDA, which is a proprietary model created by NVIDIA that can also run on NVIDIA GPUs only. However, we know that the newly emerging hardware are also powered by other types of GPUs, such as AMD and Intel GPUs, and we can also expect other types of accelerators make their entrance to scientific software. And so what we're actually trying to accelerate on GPUs is these so-called molecular integrals, which is the main bottleneck of one of the main bottlenecks of quantum chemistry codes, as they can formally scale as n to the fourth, and they are required to be solved at each iteration. And we are by far not the first people to be looking at this bottleneck. There were various schemes before us for executing these integrals on GPUs. For example, state-of-the-art codes such as TerraChem have been doing it for a while. And more recently, other GPU accelerated packages like Quick and Brian QC modules have emerged. However, all of them are written in CUDA and therefore are limited to execution on NVIDIA GPUs. To give a little bit of more detail of how these molecular integrals actually look like. So we start from the restricted Hartree-Fock generalized eigenvalue problem that you see in equation 1. So this is a very standard, very first step in all quantum chemistry calculations that you have to do. And here you can see the elements of the S matrix are given in equation 2. These are the so-called overlap integrals. It's one of the molecular integrals that we need to accelerate on GPUs. And the elements of the Fock matrix you can see are given in equation 3, where H core is the core Hamiltonian, also molecular integrals that we are dealing with. And the actual bottleneck is coming here in these Coulomb and exchange integrals that are more given in equations 7 and 8, which are the electron repulsion integrals, or ERIs, that do actually scale as n to the fourth. And so the default algorithm in GAMESS, which is the quantum chemistry software package that my group is developing to actually solve for these molecular integrals, is currently to iterate over the for shell. And here I'm showing the current hybrid MPI OpenMP implementation of ERIs in GAMESS. This is obviously CPU only, where the outermost loops are distributed over the MPI ranks, and the inner loops are fused together with the OpenMP collapse 2 clause. And both MPI and OpenMP layers use dynamic load balancing scheme. So this part is the bottleneck with n to the 4 scaling. So we want to accelerate this part on GPUs, but we can't simply take this implementation and offload it to GPUs. And the reason is because, firstly, inside these 4 loops, there is a so-called integral screening, which allows us to remove integrals from computation that do not contribute to the total energy. And that significantly reduces the number of computations that is necessary, which is great. So we absolutely need to do screening. However, doing this screening on GPUs will lead to thread divergence. So one thing that we need to do is to take it out of the kernels. We can't be doing the screening inside the GPU kernels. Secondly, this 4-layer loop structure isn't possible on GPUs because number one, dynamic load balancing doesn't really exist in the case of OpenMP, but also there are different computational bottlenecks associated with computing these different integral types. So when we loop over these 4 shells, they are not necessarily, the threads aren't necessarily going to be the same amount of, going to be doing the same amount of computations. So we know now that we need to restructure the current codes and games to be suitable for efficient execution on GPUs. However, we also want it to be portable across a variety of hardware architectures. So my personal wish list would be to have my existing Fortran code that I could just run on whatever hardware there is and take advantage of the massive parallelism offered by GPUs. And in our initial publication, we developed these OpenMP and DO CONCURRENT kernels, DO CONCURRENT being accelerated on GPUs via this STD par clause provided by NVIDIA's compiler suits. It's known that DO CONCURRENT is Fortran standard clause that could take advantage of multi-core architectures. But in 2020, NVIDIA's HPC SDK introduced GPU acceleration, and we started this work with porting integrals on GPUs via Fortran standard parallelism. So here I'm showing the 2 versions of kernels, specifically the OpenMP target offload and the DO CONCURRENT versions. And the kernels are virtually identical to each other, apart from, basically the directive, so to say. In this initial implementation, we selected several representative kernels and created a small mini app that compared the OpenMP and DO CONCURRENT versions. What was interesting to see is that the fact that individual DO CONCURRENT kernels weren't performing so well in the beginning. And then we noticed in the output of the minfo compiler flag telling us that the way the GPU code was generated is not actually by creating a single kernel with the outer loop being distributed across CUDA threads, but what was actually happening is that specific lines of kernels of that code was being executed on GPUs. So for example, some of the old Fortran syntax, such as these continue labels that I'm showing on the bottom, weren't being properly unrolled. And so after manually doing this for all the cases of the DO CONCURRENT kernels that we developed, we observed significant speed up, and that these are the best case DO CONCURRENT kernels that we have. I also want to quickly mention that from the first implementation of these integrals in the mini app, we turned it into a shared library. It currently runs with games, but it is intended to serve as the GPU accelerated engine for any existing quantum chemistry package. The way it's structured to do so is through the small C driver interface. Basically, you can pick your favorite quantum chemistry software package that does not, for example, have GPU capabilities. In our case, I do it in games. And then to calculate the integrals on GPUs, you can call libri through this driver. In this new implementation, we further optimized both the OpenMP and DO CONCURRENT kernels, and we also enabled multi-GPU execution. It's important to mention that GPU parallelism here is determined entirely by the driver. So libri only receives the total number of compute MPI ranks from games. So for example, if games is launched with 1 MPI rank in the beginning of calculations, then libri will only use 1 GPU. If games is launched with 2 MPI ranks, libri will use 2 GPUs and so on. And now I would like to show some of the results of libri compared to other packages. All the calculations shown here were run on Summit supercomputers. So all GPUs here are NVIDIA V100s and the CPUs are the IBM Power 9s. And first, I'm going to compare libri with OpenMP target offload performance with the original pair hybrid MPI OpenMP parallel CPU code in games. And the comparisons were done as best against best, meaning for the CPU code, we used the full Summit node consisting of both Power 9 CPUs with 42 cores and 42 threads. And for libri OpenMP, we used just one V100 GPUs. And we can already observe some speedups ranging from 5.78x to 24.5x. And the larger molecular systems we are computing, the more speedups we observe with libri. Next, I would like to compare the libri DO CONCURRENT with both the game's parallel CPU code and the OpenMP target offload. So when compared to the game's parallel code, the speedups of 11.5 to 47.x are observed. We see that kernels containing low angular momentum functions, so something like 631G or PCSEC0, give higher speedups, as well as when we come to large molecular systems such as water 303. And when we compare LibRI do concurrent with the LibRI OpenMP, for small molecules, we don't see much difference, but the performance gets better and better as we go to larger systems. So we can see that we can observe speedups up to 3x when compared with the OpenMP target offload, which is pretty awesome. We also compared performance of LibRI with other free or open source GPU accelerated codes for molecular integrals. First, we compared both LibRI do concurrent and LibRI OpenMP to Quick. Quick is an open source package written in CUDA programming model. And we can see that LibRI OpenMP either performs similarly or better than Quick with speedups going up to 4x. And when we compare LibRI do concurrent with Quick, LibRI do concurrent actually performs better in all cases, and we can observe speedups up to 7.4x. And what is really remarkable here is the fact that we are comparing to a CUDA-based integral package with OpenMP and the Fortran standard parallelism, which both perform better. And so that's pretty cool to observe. And last but not least, we compare performance of LibRI do concurrent and LibRI OpenMP with the state-of-the-art CUDA packages like LibChem. So LibChem is currently the fastest code for evaluating molecular integrals, on par with TerraChem, another state-of-the-art CUDA package. And when we compare LibRI OpenMP with LibChem is consistently 4 times faster than our LibRI OpenMP target offload implementation. And this is not very surprising considering LibChem was optimized specifically to achieve best performance on NVIDIA hardware. Therefore, whenever we introduce generalized models like OpenMP, we obviously take some hit in performance, and this makes sense. However, again, what is remarkable here is the fact that when we compare LibChem with LibRI do concurrent, for many systems, LibChem do concurrent performs pretty similar to LibChem, with only major differences being observed when we go to really large systems where LibChem is up to 3.6 times faster than LibRI do concurrent. This demonstrates very well that even though CUDA should technically always outperform OpenMP or do concurrent, real scientific packages are written in many different ways using different algorithms. And in this case, we are showing that directive-based approaches and standard language parallelism may very well be a more enticing choice for GPU acceleration, offering both simplicity of writing the code and great performance. Now I would like to show performance of LibRI on the multiple hardware architectures. And to the best of our knowledge, this is the only integral package that can be executed on a variety of existing and new hardware, as well as make use of different existing compilers. Here we have split between NVIDIA GPUs, V100s on Summit and A100s on Perlmutter, with OpenMP results shown on the left, and the do concurrent results on a Perlmutter shown on the right. We used Frontier for AMD GPUs and Sunspot, a pre-Aurora system featuring the Intel Ponte Vecchio GPUs. What's very exciting is that LibRI performance on Intel GPUs is very similar to what we observe on A100s, so that's pretty awesome. Performance of LibRI on AMD GPUs is better for smaller angular momentum systems, and we would like to do better for higher angular momentum D functions or larger molecular systems. And what is really awesome is that do concurrent implementation still outperforms all of the OpenMP implementations on all hardware that we observe here. To reiterate, the goal of this development is to enable large-scale quantum chemistry calculations on molecules of unprecedented sizes. Now, with the development of GPU-accelerated molecular integrals with DO concurrent, we are ready to tackle simulation of the 1700-atom mesoporous silicon nanoparticles solvated in 4,000 waters on Hartree-Fock level of theory. And so to conclude, we developed this multi-node, multi-GPU, portable and performant integral library, accelerated with Fortran standard parallelism. LibRI achieved very similar or sometimes better performance compared to the state-of-the-art CUDA packages, and it outperforms the existing OpenMP implementations. So whenever users wish to run this, if they would like to use it on NVIDIA hardware, DO concurrent will be the default version, while if people want to run it on other hardware, OpenMP target offload would be the default version. And my one wish list would be to have atomic updates and DO concurrent. This is just my one final request, and it would be really great because currently we're still using directives to do the atomic updates. This is all in conclusions. I would like to take to thank my groups and the funding agencies and Dr. Jeff Hammond from NVIDIA, who actually gave the project idea and was guiding me through it. And now I'm ready to take any questions. Thank you.